Hello guys, welcome back to another video. Today we'll be looking at part 2 of forces, which is the final part of forces. So the contents we'll be looking at today are terminal velocity, which relates to falling objects, Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, forces of braking, and momentum. Newton's first law. Newton's first law of motion states that an object remains in the same state of motion unless the resultant force acts on it. If the resultant force of an object is zero, this means a stationary object stays stationary. A moving object continues to move at the same velocity, at the same speed, and in the same direction. Examples of this are a runner at their top speed experiences the same air resistance as their thrust. An object falling at terminal velocity experiences the same air resistance as weight. Also, if they're stationary, that means their forces are balanced, and if they're moving at a steady speed, their forces are balanced. So some other examples of Newton's first law is a person who's standing still, two forces act on him, and if he stays still, that means the forces are balanced. And if a car moves on the road and moves at steady speeds, that means the forces are balanced. Terminal velocity and falling object. So we'll be looking at the three stages of falling. So there are three stages as an object falls through a fluid. At the start, the object accelerates downwards due to the force of gravity. As the object's speed increases, the frictional forces such as air resistance or drag increase. At terminal velocity, the weight of an object due to gravity is balanced by the frictional forces, and the resultant force is zero. The weight of an object does not change as it falls, as long as it stays whole. So the size of an object's air resistance depends on the object and its speed. The larger the object or speed, the larger the air resistance. So here we looked at the stages of falling. So a classic example of this is skydiving. So it's the same principle for skydiving as well. So on the graph below, we can see how so at A, there is a large acceleration when the skydiver just jumps out of the plane. At B, terminal velocity when all the forces are balanced. At C, the parachute opens, meaning they're starting to slow down. And between C to D, it's rapid acceleration as they decrease speed to hit the ground safely. And from D to E, they're just about to go to the ground. Newton's second law. Newton's second law of motion can be described by this equation. Resultant force equals to mass times the acceleration. So Newton's second law is all about unbalanced forces. When an unbalanced force acts on an object, it accelerates. The object could speed up, slow down, or change direction. So speed up, so accelerate, slow down, decelerate, or change direction, basically. Just go in a different direction. So resultant force is mass times acceleration. F equals ma. This is where force is measured in newtons, mass is measured in kilograms, acceleration is measured in meters per second squared. The equation shows that the acceleration of an object is proportional to the resultant force on the object, and inversely proportional to the mass of an object. The acceleration of an object increases if the resultant force on it increases, and decreases if the mass of the object increases. Required practical. So the method of required practical. So usually the equipment needed is a light gate, an accelerating force, a card, and a timer. So you can find different versions of it, but this is one version. So position an air track on a bench with a bench pulley at one end and two light gates above the track. Cut an interrupt card to a length and attach it to an air track glider. Connect the glider to a hanging mast by a string the length of the air track passing over the bench pulley. Make sure the air track is level. The card will pass through both gates before the mast strikes the floor. So you have to set the software to calculate acceleration. So that's a change in velocity divided by time taken. So that's a formula for acceleration. Then you add masses of 0.98 newtons of force, 20 grams to the end of the string. Then you release the glider and record the weight and acceleration. So repeat more times to get a mean value, and then repeat the steps more times as well. So the conclusion we can make is that acceleration is directly proportional to the force exerted on the object. Newton's third law of motion. Newton's third law of motion. According to Newton's third law of motion, whenever two objects interact, they exert equal and opposite forces on each other. This is often word as every action has an equal and opposite reaction. However, it's important to remember that the forces act on two different objects at the same time. So examples of this can be applied to examples of equilibrium situation. Pushing a pram. So there are contact forces between the person and the pram. The person pushes the pram forward and the pram pushes the person backwards. So it's equilibrium. Car, tire, and a road. There are contact forces between the tire and the road. The tire pushes the road backwards. The road pushes the tire forwards. Satellite in the earth. So another example of this satellite in the earth orbit. There are non-contact gravitational forces between Earth and the satellite. The Earth pulls the satellite and the satellite pulls the Earth. So another concept in this chapter is inertia. So, and the definition of it is, it's a Latin word which means inactivity. So we use the word to mean that objects remain in their existing state of motion at rest or moving with a constant speed in a straight line unless acted on by an unbalanced force. So if there's two containers and if you wanted to know, so one of them was full, one of them was empty. If you want to know, you have to figure them to know which one's full. So that's inertia. Forces and braking. Stopping distances. In an emergency, a driver must bring the vehicle to a stop in the shortest distance possible. So equation for this is stopping distance is thinking distance plus braking distance. This is when thinking distance is a distance a vehicle travels in the time it takes for the driver to apply the brakes after they realize they need to stop, and braking distance is the distance a vehicle travels in the time after the drivers apply the brakes. So there's before applying the brake and after. Thank you for watching. I hope you enjoyed my video. Please like and subscribe to my channel.